But life goes on. So here's what we're going to do. Okay? Each day, I'm going to give a short presentation, about 5-10 minutes, maybe about 10 minutes a day. I'm going to solve a problem or two. Leave your notebook out so you can take notes along the way. I will go fast. Okay? You're going to have an assignment. Should take you about 30 minutes of time each day. Just take a picture of it, submit it to me before the next class. We'll grade it. Okay? If you have questions about the assignment, do not hesitate to email me. I'll be as responsive as I possibly can. And as time goes on, I'll take feedback from you. How can these lessons improve? One thing that's happening as we speak is that they're talking about pushing the AP testing to an at-home version for you. I'll try to make sure that we can get through the material so you can get there for that. Okay? So, today, we're going to talk about sound. The reason we're going to talk about sound is because we've been talking about waves. And if you recall, we said that the wave speed equation was this. This is a toolbox equation for you guys. Velocity equals frequency times wavelength. Okay? We got lambda over here. That's going to represent our wavelength. Frequency we're going to measure in hertz. Velocity is in meters per second. Okay? So waves turn out to be a very nice representation of this. So when we look at human hearing ranges from 20 to 20,000 hertz. So let me just kind of illustrate that a little bit. So if we look at sound, and I'm going to represent this as a sine wave, as you can see here. But let's think about sound. The reason why sound works the way it does is because it's actually particles colliding with each other. Remember, the energy of a wave is what travels, not the particles themselves. If you look at these red particles, you'll notice that they are vibrating about an equilibrium position. It's the energy that gets carried, and we've got zones of greater compression and rarefactions. That's going to be represented by the crests and troughs on this graph. But let's play a tone here, okay? This tone represents the frequency of these waves. Might even be a little bit loud for you, maybe not. But what I can do here is I can change this amplitude. It's going to make it a little bit softer. And I can change the frequency. And the range that we can hear as humans is as low as 20 vibrations per second up to about 20,000 vibrations per second. But as you age, due to environmental factors, you slowly lose this upper end. And right now, even myself, I'm probably only about an upper range of about 14,000 hertz. And many of you might notice that you're losing it as well because of those earbuds that you've got in. Okay? So, that is going to be the speed of sound. And let's turn this off. And let's go back here. So if you look at the whole range of human experience, okay, we have both intensity, which we're going to talk about in the future, and the frequency. So here's 20,000 hertz, here's 20 hertz, and you'll notice that this is going to be kind of a broad expanse here. Most of where we talk is actually kind of in this narrow band here. Doris Gruber is high frequency, high volume, she's up here, but this is the normal vocal range, okay? Now, if we want to look at how fast a sound wave travels, it's affected by the temperature. And we can use this by taking the average speed of sound at 0 degrees Celsius, or in this case, we're going to use 273 Kelvin. We're going to take the square root of what the actual temperature is that day, divide that by 273 Kelvin, multiply that times 331 after we've taken the square root. This is going to be a toolbox equation. Notice, the higher this speed is, the higher this temperature is, I should say, if it's greater than 273, that's going to increase the speed of this wave. We've got faster moving particles at higher temperatures. If this number drops below 273 Kelvin, then it's going to decrease this velocity. So if we look at solving a problem like this, not too hard. On a hot summer day in Arizona, temperature reaches 319 Kelvin, which is about 114 degrees Fahrenheit. What's the speed of sound at this temperature? We're going to guess, as always. Here's my temperature. What's my velocity? That's my unknown. I'm plugging in my values. 319 is my temperature compared to 273. We know that the velocity of that wave is going to be faster than the 331 because our numerator is bigger than our denominator here. When you crunch the numbers, the velocity ends up being 358 meters per second. Okay? Not too hard of a problem to solve. But something also can play a role, and that's called the Doppler effect. Let's say the speed of sound is constant for given conditions. That doesn't mean that the frequency and wavelength won't change based upon motion. Let me show you what I mean by that. Let's say we've got a fire engine that is approaching you. Okay? Think about what that is going to sound like, and think about it as it passes you. So here the fire engine is approaching. It's taking a while. But then as it passes, notice the change in pitch. And that's because of the Doppler effect. So why does the Doppler effect happen? Well, if I've got a stationary object, it's giving off a sound wave, and the sound is radiating out in all directions, and it's traveling the same speed in all directions. But if this object has a motion, the wave still propagates at the same speed, but now since it's traveling in the direction of motion, an observer on this side is going to hear a higher frequency and a shorter wavelength. It travels at the same speed, but if the frequency goes up, the lambda has to go down. So on this side, you're going to hear a higher frequency. On this side, you are going to hear a lower frequency as a result. So the equation for that looks like this. Again, another toolbox equation. The frequency that an observer is going to hear is going to equal the frequency that the source is giving off times this, what's in the parentheses here. This is the velocity of the speed of sound in air at that temperature, plus the velocity of the observer in the numerator, and minus the velocity of the source in the denominator. Now we have to be very cautious about our signage here, and you're going to see what I mean in a second. So, O stands for the observer, S stands for the source. So let's look at a problem here. An ambulance is traveling down the highway 33.5 meters per second. It's emitting a frequency of 400 hertz. A car traveling in the same direction ahead of the ambulance is traveling at 24.6 meters per second. What frequency is a driver in this car going to hear as this ambulance is approaching from behind and as it passes and going off into the distance ahead of it? We're going to assume that the speed of sound of air on this day is 345 meters per second. Okay? So here are our givens. We have to be very cautious here with our signage. The velocity of the source is moving towards us, so that's going to be a positive value. The velocity of the observer is trying to move away from the source, so that's going to be a negative value. So when we solve this problem, we're looking for the frequency that the observer is detecting. We're going to take the speed of sound of air in this day, which is 345. We're going to crunch these numbers in. The frequency of the source is 400 hertz. We have to take into account here that in this case, this observer, I have this backwards because I solved the second problem first. Let me reverse that a little bit. Erase that. Erase that. This is actually going to look like this, okay? For this problem. For the first problem, when it's approaching from behind. So if this is the case, you'll notice that by decreasing the numerator, that actually has the effect of decreasing the hertz. But in the bottom, I'm decreasing the numerator by, or the denominator by a greater value. So this is going to end up increasing the frequency. So the frequency that the car driver is going to hear as the ambulance is approaching from behind is 411 hertz. That's what they're going to perceive, even though the ambulance is really, if it were stationary, we're giving off 400 hertz. If we reverse this, once that ambulance passes, now we have to change these up a little bit. Now this is going to end up being a positive because now the car is actually approaching the ambulance from behind, And now I'm going to be subtracting a negative because now that ambulance is going to be receding off into the distance. If that's the case, now when I crunch the numbers, that ends up being a frequency of 391 hertz that the car driver will hear. Okay, so those are 2 quick problems. That's going to end the lesson. The assignment's on Google Classroom. If you could finish and submit that to me by the time our next class starts, that'd be a great way to spend your day today. Have a good one, guys.